Okay, all of the slides and links for this talk are at the Amsterdam short URL. Cool. So hopefully throughout this talk, I won't have to say HTTP2 very much because it's been declared that we can now say H2 and save us all some pain. A lot of the figures from this talk come from this book. This is a book by Ilya Gregoric. If you like this stuff, I highly recommend picking up a copy. It's great stuff. About me, like Steve said, I'm the director of engineering at Attend. I was formerly a performance engineer for a couple years at Etsy, and I started the Boston WebPerf meetup group. My goal today is to convince you that you should start rolling out H2 as soon as possible. So the first step in demystifying SPDY and H2 is to explain the difference between them. Essentially, SPDY was an experimental protocol developed at Google, and the H2 working group was a reaction to that work being done on SPDY, so it could become a standard and rolled out more widely. So this is H2. It's the official second major version of HTTP based upon SPDY. If we look at their future, H2 has been approved by the IETF for publication as a standards track RFC, which basically means it's done. And SPDY is going to go away in favor of H2. To get some context on when, Chrome's going to remove SPDY support and only support H2 in 2016, early 2016. So for the remainder of this talk, I'm going to try to say H2 consistently. If I accidentally slip in SPDY, it's a little easier to say. Just know I'm kind of using them interchangeably unless I'm specifically saying one versus the other. Another way to look at this, from Mark Nottingham, HTTP2 is done. He is the chair of the IETF working group, so he knows what he's talking about. If we look at support, there's an important distinction to make here. If you look at support, you'll see numbers for both SPDY and H2. So here are the SPDY numbers. Browser support is quite good. The latest version of all major browsers support SPDY in this case, and the global support is around 80%. If you look at the H2 numbers, you can see support is actually a bit lower because people are transitioning from SPDY support in the browser world to H2 support. So global support is around 63%. So as we'll get into this more during the implementation portion of the talk, but for now, just understand that as browsers transition from SPDY to H2, there's a little bit of lag time where the support for H2 needs to catch up to SPDY support. And we'll dive into more details on that later on. You may have also noticed that IE11 has partial support. What this means is that it supports H2 on Windows 8 and later, but not on Windows 7. Okay, so let's get into the details of this. To talk about HTTP, we first need to understand where it fits in the network model. HTTP is an application layer protocol, which is the highest level in the stack. And this model is why people will often say things like HTTP sits on top of TCP. So to deliver the best possible experience to your users, you need to have an understanding of both TCP and HTTP, the two core protocols that involve delivering content on the web. So we're going to talk about both of those protocols today. Since TCP is lower in the stack, we're going to start with that first. Here is the standard three-way handshake for TCP. When you talk about TCP, you're going to see the ubiquitous time sequence diagram, which is what this is. It shows the sender on the left, the receiver on the right, with time flowing down the page. How many of you have seen this type of diagram before? All right, that's most of the room, so we'll fly right through this. So the three-way handshake is started by the sender, SYN packet, SYN ACK from the receiver, and then an ACK with the application data as the third piece of that three-way handshake. And this is typically an HTTP request on the web. On the left here, you'll see that this is the 28 millisecond round trip time. So the time it takes for the sender and receiver to have one round trip communication. It's a measurement of the latency between the sender and the receiver, and it is the cost you have to pay before you can send a request. So let's see a real example. It's not so bad. Light is fast, right? Well, this is a real-world example. Let's imagine we're sending a packet from where we are now in Amsterdam to my hometown of Boston. This trip is 5,555 kilometers one way, convenient number, and the speed of light is 300,000 kilometers per second. So if you do the simple math here, you might assume that the round trip time is something like 37 milliseconds. How many of you think it's around 37? Nobody? All right, how about 50? 75? More than 75? Okay, all right, so the actual round trip time is around 76 milliseconds, if you look at global ping statistics. This is actually pretty low for this distance. This is probably data center to data center, and it's not showing the last mile latency, would be my guess. We also benefit from most of this distance occurring on a high-speed undersea link under the Atlantic Ocean. So why is it 76 and not 37? We're not taking a direct path. The speed of light in fiber is about 35% slower than it is in air, and network equipment adds small delays. And it also gets worse because of something called TCP slow start. Raise your hand if you've heard of this. All right, that's fewer people. That might be 25% of the room. So here's the time sequence diagram to kind of show this. Basically, TCP slow start is a way to avoid network congestion. It's an algorithm that limits the number of packets that are in flight, and it increases that number exponentially until there's packet loss and then backs off. The goal here is really to avoid flooding a network with packets and causing degraded network conditions. So you see our three-way handshake, you see a get for a file, there's some request processing, we send 4 segments back, those are ACT, then you send 8, those are ACT, and you send the rest to the response in this case, which is 3 more. If the response was bigger, it'd go from 8 to 16. This particular example is assuming an initial congestion window of 4 packets. You can see that 4 segments initially. Now it's typically 10. On more modern OSs, you'll typically see a 10 packet congestion window to start out with, which helps us open that window a lot faster. Now, if we didn't have slow start, we could risk a condition called congestion collapse, where there are so many dropped packets and retransmits that the network conditions are severely degraded. And I'll quote an RFC here. It says this condition is stable. Once the saturation point has been reached, if the algorithm for dropping packets is fair, the network will continue to operate in a degraded condition. So this is not something we want to have happen, and this was actually observed in 1986 in the early internet. So as a result, we have slow start. The way to think about this is if you're on a busy highway in a traffic jam, and there's still cars coming onto the highway from the on-ramp, that traffic's never going to stop. You're dumping more vehicles onto a clogged roadway, and the traffic jam is going to perpetuate. To see this in our web packet example, this is the exponential growth phase on the left, where you see the packets, the window size is increasing exponentially. We have packet loss, and then we back off multiplicatively, and then we do some more increasing over time. So you'll see this sort of sawtooth pattern in the window size of your TCP connection. What this really means is it's a measurement of the number of packets that it can be in flight, and at the beginning of a new connection, that throughput is highly limited. That's not so bad, right? Because you only pay that cost of the initial connection setup, which might only happen, once per page? Anybody want to hazard a guess at how many connections we open for velocityconf.com for the Amsterdam homepage? 30, 50, 60? Okay, so here's the connection view from Web Page Test, which shows all the new connections. Now, unfortunately, this is not all of them. Let's see. About 67, so the people who said 60 are pretty close. If you think this is a particularly bad example, and it's not representative of the internet as a whole, let's look at a highly optimized page. So this is youtube.com. It's the highest traffic site on the internet that actually has a real content on the signed out homepage. And even YouTube makes 30 connections on a single page load. This means 30 three-way handshakes, 30 TCP slow starts, and as you can see by the lock icons on the left there, 30 TLS negotiations. And it's really 29, and the first request here is actually a redirect from HTTP to HTTPS, but still, that's quite a bit. Now, the eagle-eyed among you may have noticed that the browser is opening 6 connections to each domain. And you might say, what is this about? Why would we do this? Well, to understand why browsers do this, we need to talk about HTTP head-of-line blocking. In simple terms, it means that a slow request is going to block all requests behind it on the same connection. So imagine you're at the grocery store, you're ready to pay with Apple Pay, and the person in front of you whips out a checkbook. That is head-of-line blocking. So we're moving up the stack. We're going from TCP to the HTTP world. And this should be a little more familiar to folks who work on the web. So head-of-line blocking, we've got a three-way handshake. We send a GET for some HTML and some CSS. The server processes those requests, and then we send back the responses, HTML and CSS. Now, if that HTML response is slow for some reason, that CSS request just has to wait. It waits on the server until that HTML response comes through the connection to the client. You might be saying, what about pipelining, if you've heard of HTTP pipelining? Well, I'll quote Ilya here and say that if the web browser is the primary delivery vehicle for your web application, which for most people it is, we can't count on pipelining to save the day to help with performance. So if you want to read more about this, that short URL at the bottom of the slide can help you there. So back to our connection view, right? We've got 6 connections being opened to the same domain. Browsers do this to avoid head-of-line blocking. You have 6 TCP connections. You can download 6 resources in parallel on those connections, and you still have chances to block, but if you block on one connection, you can download the resource on another connection, so it's not a huge deal. It mitigates some of the risk of head-of-line blocking. The end result is a steeper waterfall where many of the resources are fetched in parallel. Let's go into some of the workarounds for head-of-line blocking and some of the downsides to those workarounds. We just talked about one of them, which was multiple TCP connections. The downsides here are extra resource utilization, both on the client for opening those connections and on the server for maintaining all those extra connections from the different clients. you also get bandwidth competition among the connections. Just because you're opening 6 connections to the same domain doesn't mean you get more bandwidth. So you're going to have competition across the different connections. The second workaround you'll see often is something called domain sharding. Now, this basically means you're going to have your resources being served from 2 different domains. You get 6 connections to domain 1, 6 more connections to domain 2. So you can get 12 connections for those resources. Now, this is a solution. You do pay a cost here. You pay for those extra DNS lookups, and you also have some additional implementation complexity to actually get domain sharding to work properly. So HTTP head-of-line blocking is one of the key limitations of H1 that H2 addresses. And it addresses that through something called H2 multiplexing. And finally, we're talking about one of the main benefits that you're going to see in H2. So how does this work? It's actually pretty simple. Through a new framing layer, H2 lets you interleave multiple requests and responses on the same connection. So this completely eliminates head-of-line blocking. And I think an image here will help explain this. So you can send a stream with data and a different stream with headers and data and completely interleave those streams in different packets on the same TCP connection, and the client knows how to reassemble those on its side. So if you have one stream, one file that's taking a long time to send from the server for whatever reason, you just send the other packets with the other data for a different stream, say a different file or a different request. Those will come back to the client reassembles all of them, and once it has a full response, it can show that in the browser. Now, this is huge because it makes the overhead of a request much less expensive and lets us remove a lot of the hacks that are best practices under H1. This is what Steve talked about in the introduction. There are a lot of things that we do today that are optimizations that are actually anti-patterns under H2. So you can forget about combining CSS and JS files, and I'll go into more detail on that later. Forget about inlining small CSS and JavaScript. Since you can keep them out of the page, you can cache them, you can multiplex them across the same connection, there's no real benefit to inlining them. No more image sprites, no more data URIs, which are kind of an anti-pattern now anyway. And then we can remove that domain sharding we talked about as well. Some people might be saying, what about headers? We still have to pass the headers for all of these requests. So yeah, we can uncombine all of our images, but we still have to make these request response cycles and have all these HTTP headers for the request. So this is a problem because verbose headers are another reason why requests are expensive, because there are a lot of extra bytes sent with each request, many of which can be redundant. Let's see this in action. Here are the request headers that my browser created when I tried to get jQuery from the VelocityConf website. And then here are the response headers for that. And this isn't small either. This by itself might not be an issue, but the problem is that I'm about to make another request for a second JS file on the same page, where almost all of the bytes are duplicated. Here's that second request, and let's look at the difference in bytes. The only thing that's different between those two requests is the URI. Everything else in the request headers is identical. So here's where the second big improvement for H2 comes into play, and it's called HPAC. HPAC is basically a way to compress headers. It's a header compression algorithm designed specifically for H2. The way it works, again, is fairly simple. You have your request headers. They get mapped to this static table and dynamic table. The static table is effectively going to be your standard HTTP headers, and then you have a dynamic table for custom headers for the given site. And then those get encoded. And so what's basically happening is that any new headers get sent. Any headers that are the same as the previous header just get referenced in that lookup table. So why HPAC and not something like zlib? Well, a crime attack showed that when you have zlib plus encryption, you can get session hijacking. Basically, by comparing the response sizes of content that was compressed versus not, people could decrypt that content. So they wrote HPAC to attempt to address that problem, not have a security flaw, but still get most of the benefit of compression. Let's see how it compares to zlib. Here's a graph of essentially compressed size in bytes of headers over a certain number of requests. So you can see that under H1, we've got quite a bit of header bytes. H2 and SPDY3 are almost the same. So SPDY3 is zlib, and then in H2, we're using HPAC. So you can see there was a small increase in the number of bytes there, but it's almost negligible relative to the benefit we're getting over H1. So it does pretty well. There are two other benefits you may have heard about related to H2. Those are request prioritization and server push. I'm not going to go into too much depth here because it's a short talk, but essentially, since all requests are interleaved on that same TCP connection, you kind of need a way to tell the server which resources are the most important to render the page. You wouldn't want to be getting something at the bottom of the page that's filling up your pipe and not letting you get something at the top So we need a way to prioritize that, and that's what request prioritization does for us. Server push is a little more interesting. It allows you to send resources that you know the client will need later on. This could be an asset for the next page, or even an asset on the current page that has not been requested yet. Some people get nervous about this. It's really no different than inlining content, and this is important. When you inline a CSS file or a JS file or an image with a data URI, you're pushing content to the client that it did not ask for. Server push just lets you do this while still getting the benefits of browser caching. So let's go a little more in depth on server push. Resources that you send via server push, they can be cached by the client because they're separate requests. They can actually be declined by the client. They can be multiplexed across that same TCP connection along with anything else, and they can be prioritized by the server as well. And finally, in case people are worried about the security implications here, they must obey the same origin policy. So you cannot server push a resource from a domain that the client didn't connect to. So really, server push purely provides improvements over inlining content and has no real downsides, since the client retains full control over what's accepted and what it actually uses on the page. The next question that comes up often is H2 actually faster? In the case of this guy's spoiler, probably not, but in the case of H2, the data shows that it is. Here's some data from Google. This is the time from the first request byte to the onload event of the page. The median improvement ranged from around 23% to 43%, with slower connections improving even more. I also did my own test. I downloaded a pretty standard template for an e-commerce framework and ran it through web page test just to see kind of like what a standard site would look like. In the H1 view, this is the connection view from web page test, you'll see we have 6 connections, and all the resources on this page are coming from the same host, so you only see 6 connections total. In the H2 world, we go down to 1 connection. 1 TCP connection, 1 TLS negotiation, saves time on the client and saves the resources on the server. It also allows us to use our bandwidth in the most efficient way possible. If you see that bottom graph, that bandwidth graph, the green line, once we get through the initial connection, through the JavaScript, the bandwidth utilization gets up pretty high and stays high through the rest of the request. If you compare it to the H1 case, it's a little more choppy, right? As we download resources, as we're thrashing on these connections, we don't really utilize our bandwidth completely. So that's another improvement there. Looking at the stats from this, our bytes didn't change, which is expected. There's no content changes at all. This is simply a server configuration change. Our start render time also didn't change a whole lot. 5% is basically within the realm of noise. And this is also expected because H2 really optimizes the delivery of the full web page. It's not going to change your start render time all that much. But our speed index, the measurement of how quickly the page appeared to load, did improve by about 15%. So you're not going to see on most sites a 2x improvement from H2, but you might see somewhere between 15% and 50% depending on your site. And it's going to vary a bit depending on your content, but it should be a meaningful improvement for a very small change configuration-wise. When it comes to HTTPS, the spec decided not to require it, but Firefox and Chrome will require it. I think IE Edge is going to require it as well. So while it's not in the spec, the browser makers are deciding that they do want to make this a hard requirement. So functionally what it means is that if you want to implement H2, you have to use HTTPS. If you're disappointed by this because of the overhead, I suggest looking at istlsfastyet.com. The short answer here is that, yes, it is pretty fast. If you optimize it, TLS is not going to add that much overhead, especially in an H2 world where you only pay that cost once for the page, and potentially an even lower cost on subsequent page loads on the same site with things like TLS session resumption and session tickets. If you have not rolled out TLS yet on your site, there's a new project called Let's Encrypt that's about to launch free automated TLS certificates. So definitely worth a look if you're going to do this. They're planning on launching this quarter. So this is definitely worth looking at if you don't have certs today, or even if you have certs today and are paying a lot for them. So far, it's been all puppies and rainbows. What about some criticism of H2? There's 2 things you hear a lot. The first is it was rushed and we wanted more. So my attitude about this is that something good now is better than something perfect 5 years from now. You might also hear people say, why does it require TLS? Well, as we talked about, the spec doesn't and some browsers do. Really, all the browsers are going to. Now, the TLS requirement is interesting from browsers, and I think there's a couple important things to talk about here. One is the security, which is obvious and helpful. But the second is actually an implementation detail. there's a lot of intermediary proxies between your server and the client that like to inspect content and manipulate it in some way, shape, or form, right? If you encrypt that content, they can't do that. Why this is important is because if that proxy doesn't understand H2 and then tries to intercept your request response cycle and manipulate the content somehow, but doesn't speak H2, you could end up with a failed request. So encrypting that request, what it means is these proxies can't peer into the content. It can't screw up that H2 connection. So it actually makes the rollout a lot easier because the server and the client are the only people talking H2, and you know they talk H2 because they talked about it and communicated. And then everything else in the middle is encrypted. So the bottom line is that haters are going to hate, but by and large, people are pretty happy about H2. Let's go into implementation. As far as web server support goes, it's pretty solid. All of the major ones that are probably being used here are supporting H2 currently. And I'd like to note that the site that this came from is tlsfastjet.com, provides exact configuration files you need to set up H2 on Nginx. So even if you happen to be using a web server that doesn't support it, you can always put a proxy in front that's Nginx to support it for you. If we look at the Netcraft sort of survey of web servers, you can see that the top 4 on this list, Apache, Nginx, Microsoft IIS, and then of course Google, all do support H2. So support is quite wide in the web server space. One other pretty cool announcement about a month ago is that Nginx Open Source 195 did release with H2 support. It had SPDY for a long time, but now they're officially switching over to H2 support. And this is both in Nginx Plus and in the open source version. Let's look at the implementation within Nginx, because it's a popular server and it's pretty simple. So here's how you enable it. This is the configuration block, and this is the change. You literally add 5 characters to your configuration block, and H2 is on. Now this obviously assumes you're already serving your site via SSL. So if you have SSL on, it's literally this simple. As I mentioned earlier, if you don't currently serve your site with TLS, you will have to make that change. What about CDN support? If you terminate your TCP and TLS connections at the edge with your CDN, you probably care about support there as well. This table is a little more sparse. A couple of major CDNs have support, and more are adding it all the time. There's another CDN here, I think Key CDN, that also is talking a lot about their H2 support. So that's not on this list, but they do support it as well. Big ones here, Akamai, Cloudflare, Google App Engine, Instart Logic. There are a few here that are pretty popular that do have support. And then one of the big questions that comes up is how do you support both H1 and H2 clients simultaneously? Here's a quick cheat sheet. OK to keep, combining CSS and JS, spriting. If you already have that in place, it's fine to keep it. And on the next slide, we'll talk about why. You probably want to stop domain sharding, and you want to stop inlining content. As I mentioned with server push, there's really no reason to inline content anymore. OK, so let's dive into CSS and JS and talk about the trade-offs here. This is sort of like the more interesting part of this, because there are some trade-offs. The first one is gzip compression ratio. When I think about this, I look at a graph like this. This is the compression ratio you get relative to the file size. So this is from 0 bytes all the way up to about 100 kilobytes. Typically, these are going to be the kind of file sizes you will see on the web. The larger the file, as you can see, the better the compression ratio. And this is basically because gzip as an algorithm, the way to think about it at a really high level is there's a dictionary of symbols, and then those get mapped to smaller characters, and those get essentially mapped to the larger file. So you have a dictionary, a lookup dictionary, then you have the file that gets replaced with those smaller symbols. So the way this works is if you have a larger file, you get better compression because your dictionary can map to more of the file. And you'll even see that for very, very small files, the files can actually get larger if you gzip them because there is some overhead to that dictionary. But as the file gets bigger, you're going to get better compression. What this means is that if you combine all your files into one file, you still get lower bytes sent to the client. So even in an H2 world, combining the files can be beneficial for this reason. There's also file I/O. Now, this is typically not going to be an issue for most folks, but if you happen to use a really high traffic site and you have 500 files that you want to serve, combining them may actually reduce your file I/O in a non-trivial way. So there's some benefit to combining there as well. Header overhead with HPAC, this is going to be very, very small, but it's non-zero, right? If you have 100 files or 500 files, which some people do, combining them is going to reduce that header overhead. On the flip side, we have caching. And this is why you'll hear people say, well, if you have your files combined, you should split them out again, because the more granularly you can manage browser caching, the more effective that caching is going to be. If you combine everything into one file, every time you change that file, presumably you're going to hash the contents in the file name in some way to bust the cache. So every time you change that file, you're going to blow that browser cache and make the user download your entire JavaScript payload again. So that's the downside of combining everything into one. One compromise I'll typically see people do here is they bundle all of their third-party scripts that aren't changing very often into one file. All of your in-house code can go into another file. And that way, when you change your in-house code, you're not blowing your cache on your third-party scripts. And so this is going to be customized given the content on your site, but that's a decent rule of thumb, right? 2 bundles is still going to be fine. It's going to work great for H1. It's going to work great for H2. The second thing I want to talk about here is domain sharding. We talked about how we should take this away for H2. If you happen to have domain sharding today and you know that it's having a big impact on H1 connections, you can still get the benefits of sharding without hurting H2. And it's a 2-step process. Number 1, if the 2 domains that you're sharding across map to the same IP, and then number 2, you have a wildcard TLS certificate that covers both domains, then H2 is smart enough to use one TCP connection to both of those domains. So if you do these 2 things, in an H1 world, the browser will still open those extra connections, so you get the benefits of sharding. And in H2 world, it will be smart enough to use one connection for those domains. So you do get it's kind of the best of both worlds. The one caveat, of course, is that with the sharding, you will still have to do both of those DNS lookups. So it's not perfect, but that can be an option as well. If we go back to our support diagram here, when you think about supporting both H1 and H2, just remember that since almost 80% of clients globally support SPDY today, you can pretty safely remove most of those H1 specific optimizations once you have SPDY or H2 deployed. Yeah, just this global number here, this 80%. That's what I'm talking about. Yeah, so this is kind of what I mentioned earlier. Like there's a transition period from SPDY to H2. So SPDY is at 80%, H2 is at about 63. As I said, in the spring of 2016, Chrome is going to remove support for SPDY. So if you're thinking about deploying this today, it's probably going to be SPDY for the remainder of the year, maybe a little bit into 2016, and you'll cut over to H2 in the spring once SPDY support starts to get dropped. And we saw that Nginx config, if you happen to be using Nginx, it's just you write SPDY there instead of writing HTTP2 there. So it's pretty simple. You'll have to think about that for your site. All right, so to wrap up, takeaways, H2 is here. H2 is fast, it's supported, and you should go implement it. Thank you. We do have a few minutes for questions.
How do you upgrade an H1 to H2 request? So you have a website which supports H2.
Yeah.
And you should decline, oh, guys, go to H2.
So the question is, how do you upgrade an H1 request to an H2 request? If you have a server that supports it, how does the client do that negotiation? So that's all handled by the browser itself and by the server communication. So like if in the Nginx case, you just write HTTP2 in your config and you turn it on. The server is smart enough to negotiate with the client, figure out if the support is there with no extra round trips over what you already need to do for TLS, and then it'll figure out which connection it should use. So there's no implementation complexity there. Like literally the implementation on the server side and the client side will do it for you. So you don't have to worry about it. So the same, yeah, so an H1 only client can connect to your Nginx server that's communicating over H2. It'll be fine. It'll downgrade H1 without a problem. No redirection, yeah. So that's one of the nice things about this TLS extra round trip. Within that TLS round trip and the handshake, it can negotiate and figure out which protocol to use with no extra work. Yeah.
How does request prioritization work? Where do I have to implement it?
Yeah, request prioritization. How does it work? That's on the server side. So it's one of those things that's like still kind of rolling out. Not every implementation is going to have that built in day one. But it's something that you can give hints on the server, and I think the client can also ask for things as well. But it's something that's like still in the early stages, which is why I didn't spend as much time on it. Today, people are mostly focusing on the multiplexing and then HPAC to get the most benefit today. Yeah.
Are there already tools where I can use for debugging? So for example, today when I use Wireshark, it's very plain, but there is a multi-text version and compressed version, so I think it's more.
Yeah, so the question is basically, is the tooling good enough to handle this new protocol, right? Because it's a binary protocol, it's not a text protocol. So if you're using something like Wireshark, you used to be able to just look at the request and response cycle right within your packet capture tool. The tooling is catching up. There's definitely some decent tools out there today. It's going to take a little while before you have the full tool coverage that you have for HTTP 1 today, but that is a problem that tooling will solve. Yeah, you're right. I mean, certainly if you're looking at the raw stream on the network, you can't just visually look at it like you can with H1, but that's something we can solve with tools. Yeah.
There's one of the performance rules is document flush,
Mm-hmm.
so that you can send the top of the HTML document down, get the browser going,
Mm-hmm.
while you take time to stitch together the rest.
Yeah.
Does that still work in H2?
So the question was, one of the performance rules is like early flushing of the content, right? You flush the first few bytes of the content so the client can start downloading those resources first. Will that work in H2? You certainly can do it. I think it's important to note there are a couple downsides with that. One thing that I've seen in the past with that, when you flush the head of the document down, you typically send a 200 to the browser. So if you need to redirect later on in the cycle, you can't do that. Or if you need to throw an error code, you can't do that. But yeah, you're right. You can certainly do that. And one of the other things that's good to note here, you can also just enable H2 for your static content, and your dynamic content on H1 could still come off a domain that's only H1. That could be flushed to the client, and then as it gets the CSS and JS, that could all be served via H2. So if you want to kind of roll this out in pieces, that can be a nice way to avoid some of the implementation complexity, and just do it for your static resources, which is the vast majority of the page and where you really want to have H2 because it's going to have the most impact. But yeah, it'll work in both cases. Yeah.
What about non-browser traffic, like REST-like services and all that stuff? Is there any advantage in?
So yeah, the question was about what about non-browser traffic? It really depends on how TCP connections are being opened, right? So depending on the flavor of traffic that you're using, let's say you're not in a browser context, it's a REST API or whatever the case may be, you kind of have to look at when the client is opening a TCP connection to the server. So really the way to think about it is that the benefit of H2 is sending multiple things on the same connection. So if you have a persistent connection via TCP from your client to your server, then H2 can provide an advantage there as long as you're going to issue multiple request response cycles over that one connection. If it's a one-off request and there's nothing behind it, you're not going to get a lot of benefit because there's no subsequent requests to benefit from HPAC, and there's no subsequent requests to benefit from multiplexing. So it's really about sending more than one request on the same connection.
Do you know any libraries that have implemented that? Like backend?
Yeah, libraries that have implemented that. I mean, certainly if you're talking to an Nginx server, like it'll just do it for you, whether it's a browser or not. You just have to make sure that your client can support it as well. So if the client's not a browser, that client has to support it as well. Anything else? Yep. Does keep alive header still have a meaning? It does, yeah. I mean, certainly you wouldn't want to close that TCP connection prematurely, especially because it's one connection. So you want to make sure you're only paying that upfront cost of the connection and the TLS negotiation once. So keep alive does matter. Yeah, so the point there is to not prematurely close the connection, basically. And you can make sure that still happens with keep alive. Yeah.
Is HTTP 2 working with a main domain in example.com and static resources on another domain.com
Mm-hmm.
with a certificate which is signed for both domains with a subject alternative name?
Mm-hmm.
Is it working?
Yeah, so the question is if your base domain is on, say, www.attend.com, and you have your static resources at some other domain, right, static.attend.com, but you have a cert that covers both domains, will H2 work across them, right? So it comes down to the fact that the cert has to cover both domains, and they have to be on the same IP address. If they're on two different IP addresses, then it's going to make two connections. But yeah, so it's actually in the spec. If you have the same IP for two domains and the same cert, it's in the spec, and the implementations do follow this, that it'll make one TCP connection to that IP. Yeah, because TCP is essentially like low enough in the level that it doesn't care about DNS. It just talks to the IP address, so it can make that one connection, and then it can figure it out and make all the requests over that one connection. All right, I think it is beer time, so we'll take one more question and then we'll move on. Yeah.
Sorry, everyone.
Yeah.
How many connections can be multiplexed via one?
How many connections can be multiplexed? So how many like streams can be multiplexed? I don't know if the spec specifies an upper limit. I bet that's a client library type thing. But yeah, it's limited by bandwidth, basically. Yeah. All right, thanks. Enjoy the evening.